All right, so this is the lab we would normally do where you'd all get cups like this. So I'm going to take a little data. We'll have Amanda be the first trial, and then we'll have Gabby since it's alphabetical order, and then Mr. P was the third trial. Okay. Amanda, what volume of hot water did you get?
75.
Oh, it's 75, okay. And so you got the same with cold. I asked them to get the same amount of hot and cold. Gabby, what'd you get?
75.
You both went for 75. Look at you nerds, splitting the difference. Okay. All right, wonderful. I'm going to go ahead and get the temperature of Gabby's water here. Let's see. We're going. I'll get them both at the same time. How about that? So let's see here. Looks like Gabby's hot water is 26.4. So the temperature of her hot is 26.4. Temperature of her cold, we're coming in at 22.0. I'm going to go ahead and mix these two waters, and we'll check their temperature here in a second. Amanda's hot and cold. Plop. Amanda's coming in with, let's see here. Oh, your hot got hotter. Look at that. Her sink must have been better. Let's see here. Well, her cold is looking at 22.9er. And her hot is, we'll call that a 29.6. And I'm going to mix. Kind of stir that around, make sure they get mixed nice. Okay. Now I'm going to get the temperature of Gabby's mix while we wait for Amanda's mix for a second there. Gabby's mix is coming in at, let's see here, 24.1. And Amanda over here, we're looking at a 26, let's see here, 26.2. There we go. Mr. Pilcher's data, I rocked 100 milliliters. My hot was at 58 because I heated it up more. Boom, boom, boom. Alrighty. So you would have normally collected data just like this if you were doing the lab today. Thank you for doing that, Gabby and Amanda, by the way. All right. So we're going to take a look at this here. So again, I had hot water in 1 cup, cold water in another cup. I mixed those two. Okay. So let's see here. We're going to collect a little bit more data. So with trial A, or 1, whatever, Abby, trial Amanda, or trial Abby. Her name's Amanda, and then Gabby was the other one. I just kind of mixed Gabby and Amanda. Wonderful. Okay, so we're looking at this. Her hot started at 29.6. Her mixed temperature was 26.2. So what's the difference between those two? That looks like a 3.4.
Yeah.
Yup. Her cold was 22.9. Mixed again was 26.2. And difference between these two, I don't care about the negative. I just want to know how big was that gap between those two. What was it? 4.7. Okay. All right. And then over here, 3.7.
Hold on, let me do it again.
Hold on, wait. Oh, you're crazy. It's 3.3.
Yeah.
You liar. Oh my gosh.
I did it wrong, okay?
You lied to your teachers what you did. On purpose. I know you did it on purpose. No, I'm just kidding. All right. Then we got some Gabby. Got some 26.4. The mix was 24.1. So that's a difference of 2.3. Again, I'm just finding the difference between these two. For cold, 22.0. And then we got some mixed of 24.1. So that difference is going to be 2.1. Okay. Mr. Pilcher data. Okay, I had 58 for my hot. Steaming it up. 40 for the mixed. Difference of 18. Cold was 22. 40 for the mixed. Difference of 18. Okay, so here's what we saw. We saw that the hot water went down in temperature a little bit. and the cold water went up in temperature a little bit when you mixed hot and cold water. Is anyone shocked by this? No, not at all. Why did we even do this, Mr. Pilcher? Everyone knew what was going to happen. I'd also like to point out that the volume of hot and cold was the same for all of them, so it wasn't like you had like a huge bucket of hot water with a couple drops of cold, like it was the same amount of each, okay? And you'll notice that the difference is, so if I highlight this here for you, so the difference is, should all be about the same. 3.4, 3.3, pretty much the same. 2.3, 2.1, pretty close. 18 and 18, nice, okay? So here's the idea. The hot water lost as much heat as the cold water gained, okay? So they met in the middle, so to speak. So here's a big idea. Here's a big idea. Your delta T hot, Mr. P, why didn't you say triangle? Why did you say delta? That's a Greek symbol, okay? A little triangle means delta. What that means is, from now on, just know that that means change. So if Brooke Jones is like, Mr. P, I had an A first quarter and an F second quarter. My delta was like 5-letter grade. Like, okay, she's talking about the change. Talking about the change. It's like, why did you single me out and say I have an F second quarter? Anyways, delta, so the change in temperature of the hot is equal to the change in temperature of the cold. And what this really means, the big idea, you should actually be writing down. The energy lost is equal to the energy gained. That is a big idea. Energy loss is equal to energy gained. Energy loss is equal to energy gained. Okay? That is a big idea. Big idea. This will always be true forever and ever. Mic check. Kelsey Schmidt, can you still hear me?
Yeah.
Great, okay. I get a little paranoid about the mic every now and then. All right, sweet. Okay, so now we're back on our notes. For those of you B people who didn't have a first worksheet, my bad, but now you should be good to go. All right, so ThermoChem notes number 1, baby. ThermoChem notes number 1. So we're going to talk about thermal energy, temperature, and heat. Mr. P, do I have to write all that down? No, you don't. No, you don't. And again, this is just you taking notes, so this isn't like in the packet anywhere. But we will be getting back to that packet later this period. All right. So we got to talk about a few key terms. First one, kinetic energy, baby. Kinetic energy. That's the energy of a moving object. So kinetics is talking about movement. So if you're talking about kinetic energy, something's got to be moving, okay? So guys, maybe you remember something like this where you talk about potential energy before something falls, but while it's falling, it has kinetic energy because it's moving, that kind of thing. Kinetics is talking about movement, so kinetic energy is energy of something moving. All objects, no matter what, have moving particles. Like everything in the universe has moving particles. Good looks, Ollie. Nice.
Thank you, Ollie.
And so the faster something's moving, the more energy it has. And I'll slow down for a second here. So you may be thinking to yourself, like everything, you're like, take your little paw, slap it on the table, like, I can really feel the particles moving. No, you can't. You're lying about that. But the idea is, even though when you have like a solid, like your desk, you're like, well, my desk isn't like going anywhere. Like last I checked, I feel like it's not really moving. The little particles inside of the desk, what they're doing right here, is they're not like, here, watch my fist, okay, see this? See how it's sort of shaking? It's not like going anywhere, but it is moving, right? That's exactly what all the atoms of your desk are doing, okay, in a solid. They're not really going anywhere, but they are moving all the time. And so everything has kinetic energy of some kind in that way. And the faster something is moving, the more energy it has. Which kind of makes sense, right? Okay, a cheetah going 1 mile per hour has less energy, kinetic energy, than a cheetah going 50 miles per hour. Pretty straightforward. But that brings us to thermal energy. Thermal energy. That is the total kinetic energy of all the particles in a substance. So again, if I was taking notes, I would just emphasize total kinetic of all particles. So you take the kinetic energy of every single particle, every little shaking atom or whatever they're doing, you add it all up. That is the thermal energy. And its units are joules, or capital J. Like what my grandma wears? No. Like some dead dude's last name was Joule. That's where it came from. And so you're going to see a capital J all the time. We're going to be slapping J's on everything in this unit, okay? So like when you're finishing up a problem, you're going to be like 1.67892 J, and you put a capital J, you box it up, mic drop. That's how your problems are going to be. Now, because thermal energy is when you're adding up all the particles, that makes it extensive, okay? Thermal energy is extensive. It's extensive because it's adding up all the particles. So if you have less particles, okay, so we take Ailey's desk over there and we chop it in half, she has half as many desk particles, okay? And so the thermal energy would have been roughly cut in half, okay, because we lost half the particles. So thermal energy is extensive, and the mass does count. Again, do I have to write mass does count? Like, well, if you know what extensive means, probably not. Because you're like, yeah, that's what extensive means. So here's a question for you. Let's say I've got a big old iceberg versus a hot cup of water. Which one has more thermal energy? Yes? The big iceberg. Okay? And it's a little counterintuitive. If I asked you guys this before I explained to you what thermal energy was, most of you probably would have said this little guy. But here's the idea. Even though this temperature might be a little higher than the iceberg, there's like millions of more particles in the iceberg, and those are going to add all up, and you're going to have a lot more energy in the iceberg, thermal energy in the iceberg. So this guy's got way more energy, thermal energy, okay? Because it has so many more particles in it, so many more H2Os are in an iceberg than in a tiny little cup of hot water, okay? Even if you have a mug as big as Mr. Campbell's. Anyone have Mr. Campbell? Well, you're in for a real treat someday if you ever have Mr. Campbell for ecology or zoology. Good times. Okay. All right. So, again, we have a little bit of an overload with the terms at the very beginning. As you guys know, when we start a unit, we kind of have to get on the same terms. We're like, okay, this is what this means, this is what this means, and then we sort of explore them. So, conduction, convection, radiation, okay. So, you guys maybe heard these terms before. Conduction, that's the transfer of energy from particle to particle, so stuff's got to be touching kind of thing. So energy from this handle is going to be jumping from particle to particle as it's getting closer to the end of the handle. So things must be touching for conduction to go down. Okay. So if I wanted to transfer some thermal energy to Jeremy right now, I couldn't do it because him and I are not touching, okay? I'm sorry, we couldn't do it via conduction, I should say, because you have to be touching. Jeremy could send some thermal energy into his desk, though, because he is touching his desk. Then we got convection. That's a transfer of energy in a gas or a liquid. So you need some movement of currents. So in this little pot up here, convection, okay, so you have hot water at the bottom. You got cool water at the top. Okay, so thermal energy can be going up towards this top of the pot. Okay, through the water, and that would be an example of convection. Then you also got radiation, and that is where thermal energy is transferring through electromagnetic waves. It doesn't need any particles. This is how energy can be transferred through space, like outer space, not like space, like volume. Like outer space where there aren't really any particles for it to jump. In other words, this is how the sun heats us up. Okay? So the sun is sending thermal energy via radiation until the moment it hits our atmosphere, and then it has some air particles to work with. And then we're looking more at a convection type situation. That's how the thermal energy from the sun is heating us up right now. Mostly through radiation. For all those billions of miles in between us and the sun, where there's just empty space for the most part. Okay. That's your conduction, convection, and radiation. Good times. Woo! All right, check that little paw out. You know, has a lot of notes just now. Need one of these. Do that. The bro snap. Pretty good, right? Gotta get a really wobbly finger. Look at that. Look how my wrist isn't like moving, but my finger's all. It's crazy. Anyways, wow, Mr. P, you're like really cool. Why don't we just get this class over with? Okay. All right, good talk. Mic check, John. Can you still hear me? I stepped on the wires. I'm a little worried.
I can, Mr. P.
My God, that's the enthusiasm I'm looking for on a Monday, John. Let's go, baby. Talk about the law of conservation of energy. You can't create or destroy energy. Not possible. Can't be done. Can't be done. And that is why the heat gained of something is equal to the exact same number as the heat lost by something else. If something heated up, something lost that exact same amount of heat elsewhere. Just like the law of conservation of mass, right? Which you don't have to write this, but remember, mass can't be created or destroyed. Same thing with energy. When our universe was quote-unquote born like 6 billion years ago, whenever it was exactly, there was a certain amount of energy, there's a certain amount of mass at that time, and that mass and energy has never changed throughout the history of everything. So there's an exact amount of energy and an exact amount of mass in this universe, and those two things can never change. Can't lose either one, or gain either one for that matter. Yes, Jonesy?
How did it get there in the first place if it can't be created?
That is a great question. So that's where science doesn't really have a good explanation. So science can explain what is happening right now, but it can't explain where things started. It's a really good question. That's actually where a lot of people's faith will come in. And remember, again, do you have to write this in black? I don't think so. You probably know this from Unit 2. Remember, the mass of reactants is equal to the mass of the products. The mass before is equal to the mass after. The heat gained is equal to the heat lost, and vice versa. Alrighty. Yeah, baby. What time are you guys free for me? Oh, you're still trapped for 21 minutes, baby. Let's go. Monday. Now let's talk about temperature real quick. Let's talk about temperature. Temperature is average kinetic energy of the particles in a substance. It shouldn't say A. It should say the particles in a substance. And its units can be degrees Celsius or Kelvin. You guys are used to like, oh, Celsius or Fahrenheit. Fahrenheit's a trash American unit. We don't really like to use it very often. It's more about Celsius and Kelvin. Just in case for your own enrichment, Celsius plus 273 is equal to Kelvin. In other words, Kelvin is a temperature scale where the gaps between each degree is exactly the same as Celsius. It's just started earlier than Celsius, if that makes sense. The reason why we even have Kelvin, again, Kelvin was some dead dude's last name. The whole point of Kelvin is instead of it's 0 being when water freezes, that's where in Celsius. Like, we found out where water freezes, and we made that. We call that 0 degrees Celsius. That's where 0 degrees Celsius came from. 0 degrees Kelvin is just 273 degrees earlier, and it's when all particles in a matter just stop moving. It's so cold it just stops, which isn't possible, but it's an idea. So nothing's ever been at 0 degrees Kelvin, but yeah, something that people are trying. I don't think they'll ever be successful.
Because that's why you have to add the 273 because it never, like that's when stuff's always.
So like 0 degrees Kelvin is theoretically when all matter stops moving, and it's also the same as negative 273 degrees Celsius. Does that make sense? Yep. So temperature is intensive. It doesn't matter how much stuff you have. And you think about it, that makes sense. Okay? So if I go like this, I take the temperature of the air in this room right now. Okay? We're getting 27.9er. Okay? Now, all right, don't tell the thermometer. Don't tell the thermometer. Instead of the temperature of the air of the room, I'm just going to... It's in a cup now. It doesn't know. It doesn't know. The temperature is exactly the same. Oh. How does it know that? The point is, temperature is an average, so it doesn't matter how much or how little of the stuff you have. Temperature just seems like, well, every particle has about this much energy. That's what temperature is measuring. So that means temperature is intensive, unlike thermal energy, which is adding up all of the kinetic energy of particles. Temperature is just looking at the average kinetic energy. Okay? Again, 0 Kelvin. Do you have to know this about Kelvin? No, you don't. I'm just letting you know that's what Kelvin does mean. Again, focus on what's in red most of the time. What's written in black is not as important. I'm not going to emphasize it as much. But this right here, oh yeah, you better know that. I got in red, I put it in bold, put a couple stars around it, you know, trying to say, hey, don't forget, all right, temperature is intensive. Okay, and then here's how you can compare them all, but I don't want to worry about that for now. Not going to worry about that for now. We got to talk about Heat, baby. Heat is a sweet movie with Robert De Niro and Al Pacino. The restaurant scene's so good. I'll tell you what. What were those little paws doing? You had a little thing going over there. She's like, oh, okay, let's just keep going. All right, good talk. It's Monday. The transfer of energy from one substance to another. So when I'm talking about heat, we're talking about energy being transferred. It's on its way. It's moving somewhere. And the units will be in calories or joules. Has your Peltra like the calories in my Doritos at lunch? Kind of, yeah. We can talk about calories more later, but calories are actually a measurement of heat. They'll set your Dorito on fire and see how much heat it gives off, and that's how many calories Doritos have. But we'll talk about that later. And from now on, this is very important to me, you will speak in a direction of heat, not cold. Okay? Not cold. You will speak in a direction of heat. And I'll explain to you what I mean by speaking in terms of heat. We talk heat. We don't talk cold in this class. And heat is extensive, by the way. It does depend on how much stuff you got. So what I'm saying is, Tanner's index finger can transfer some energy, but his whole paw can transfer more. Okay? So on the test, we'll be talking about heat, that kind of thing. And then we got two more terms, conductors and insulators. Woo! Mr. Poacher, you are really just throwing way too many terms out right now. I know, but now we won't have to do after today. We'll just get past all the terms. A conductor easily transfers energy. It's like a highway for energy. Like, oh yeah, man, come on, get on the entrance ramp. Let's go, baby. We're at 65 miles per hour. Like conductors are like, let's transfer the heat, baby. Let's transfer it. Insulators are like your grandma. She was trying to teach you how to drive. Like, oh, slow down. Like, grandma, we are in park right now. Okay, like, what do you want from me? Okay, insulators really resist the transfer of energy. They really slow it down. They won't stop energy from being transferred, but they will slow it down quite a bit. And conductors are like, let's go, baby. Bring on the energy. And you're actually going to be able to explain quite a few things in your real life during this unit, which is part of the reason why I love this unit. And it's part of the reason why students will say that they think this is the second hardest unit of chemistry, but it's often one of people's favorites. Because they'll be like at home, they're like, oh, this works because of the, oh my good. It feels nice when you can explain something in a real nerdy way. And you can be like, hey mom, do you know why that worked this way? You'd be like, Like, no, why don't, are you going to tell me? And you're like, well, actually, blah, 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 blah. And like, you feel really good about yourself, you know? So you're going to have a lot of those moments to show off your big brain to your parents. Now let's talk about nature's tendency. Let's talk about nature's tendency. Heat goes from an area of high temps to an area of low temp. Or you could say an area of high average kinetic energy to an area of low average kinetic energy. Here's what I'm really trying to say, people. If you want to just draw this in a more simple fashion. H for high temp. It goes from hot to cold, quote unquote. Or what I would really prefer you to do is put an L for low temp. Because I really like the word cold. That's a bad word. Don't you say that word. Wash your mouth out with soap. So although I had those written up there before, I did that on purpose. What I really want you to think is high to low. High temp to low. And if you are a lazy individual and you just want to put a box with an H in it and have an arrow point to a box with an L in it, that's probably all I would do, on this slide. A lot of you guys are a lot more, hardworking than I was in high school, though. So, whatevs. So again, coldness, quotes, does not exist. It's just a lack of heat. It's like, ooh, I'm cold. Like, nope! You're lacking heat, sweetie. Okay? We don't have cold anymore. Not a thing. Not a thing. Although you could be like, she's so cold. But, I think that's kind of a different type of cold. Like, do you really mean that she lacks heat, or is there something else going on there? Is that what an ice queen is? All right, anyways. Okay. So let's say you're outside. I'm going to do a little drawing, people. Guys, get ready for Mr. Pilcher's art class. You want to know a true story? Mr. Pilcher's story time for 30 seconds. On Mother's Day, when I was in the 6th grade, I went to Walnut Springs, and I drew my mom a tiger. Because she was an art teacher back in the day. I drew her a tiger. So it wasn't like a circle where you could just kind of turn it whatever direction. It was like a tiger. There's one way to have a tiger. You know what I'm saying? She's like, oh, honey, it's great. I love it. And she hung it up upside down. Because she couldn't tell what it was or which direction it went because it was a tiger. That's how bad I am at art, okay? Just for the record. That's a true story. I still can't bring it up because my mom's pretty sensitive about it. But, that's a true story. She hung my tiger upside down. Like, well, it could go any other way. I was like, have you ever seen a tiger walking on its back? Because it can't go. All right. Really sensitive stuff for me. Okay, so anyways, here's me. That's me. Here I am. So I look like Gumby, all right? All right, I got really long arms. Anyways, now I'm sitting here at about 37 degrees Celsius. So are you people. It's about 98 degrees Fahrenheit, roughly. Now, if I go outside, and so today, I don't know, it's like 40, let's say it's 40 degrees outside today. Oh, no, that's 40 degrees Fahrenheit. I'm sorry. Stop. Let's say it's wintertime and it's 0 degrees Celsius outside. Okay, let's say that. Now, you may be thinking, you'd be like, ooh, man, the cold's really getting to me out here. Ah! Okay, cold is not getting to you, but what is happening is heat is leaving you. My heat is leaving me because my temperature is high, it's 37 degrees. Outside is a low temperature because it's 0 degrees. So really what we have here is a little H for high and an L for low. And so the heat for me is going to the air outside. So do not say, oh man, there's a hole in my pants and the cold's getting into my... No. The heat is leaving you through the hole in your pants. Okay? Does that make sense? Don't you tell me about cold. Cold ain't coming towards you. Heat is leaving in that situation. Yes, ma'am.
What about wind?
What about wind?
Yeah, what about wind chill?
Wind chill? So what do you mean about it? What about it?
I mean, if the wind is cold, isn't that like the cold hitting you?
No. What's really happening there is every time, so like wind is like different particles of air, they're all like flowing past you, like a little assembly line. Every time one flows past you, some of your heat jumps on, and off it goes. And the next time a little air particle comes in, whoop, heat jumps on. Like they're hopping on the bus and they're leaving. Yep. Huh? Look at you. Look at you. Yes, it is. Look. Oh. Using a term I just taught you. So good. All right. Now we're going to learn a little something. One paw. Slap it on the desk. Now slide it over to one of the wooden legs of your desk. Okay? Take the other paw and grab one of the metal legs of your chair. Harry Case, do those two things feel the same? Tell me the difference.
Chair's cold.
Yeah, it feels cold, right? The chair leg feels cold, and yet the table leg feels kind of warm. Okay, you can stop playing that. What do you call that? Twister. Yeah. No more twister. Okay. Now, originally you'd be like, oh, okay, so the chair leg must be colder, quote unquote, than the table leg. That's not true. They've both been sitting in the same room at the same temperature for months. Okay? So the table leg and chair leg are exactly the same temperature. It's true. So what the heck? Why does one feel cold and the other one does not? What's that? One's a conductor, one's an insulator. Which one's a conductor? The metal's a conductor. The metal's a conductor, okay? So the metal chair feels cold, and the wood feels warmer. They're not different temps. The metal's a conductor, and the wood is an insulator. The metal's a conductor, and the wood's an insulator. So which direction is the heat being transferred? Well, let's do a little Mr. Pilcher art time again. That's not what I want. Okay. Okay, there's me. Okay. So let's say I take one paw and put it, oh wait, no. Here we go. Here comes the paw. Okay, there's one paw. Grabbing the table leg. Other paw down here. Okay, grabbing a chair leg. Now again, I'm about 37 C. This table leg's about 23 C. So is this chair leg. So if I was drawing a heat diagram, which I'll be asking you guys to do all the time, I'd put a little H with a box right next to me. Again, this is relative. Okay. I put an L next to the table leg. I put an L next to the chair leg. So which direction is heat going? Well, here it's going from high to low. Over here it's going from high to low. Okay? So both times, heat is leaving my paw and going into the leg of either the table or the chair. It's true in both cases. However, when it's going to the leg of the table, that would be slow. Because it's an insulator. What is an insulator? So it slows down that heat transfer. That heat is going to go into that table leg. It's just going to take a while. The chair leg feels cold because this is fast. So the moment your hand touches that conductor chair leg, it's just slurping the heat right off your hand like that. So that's why it feels cold. That's why it feels cold. Make sense?